Okay, so let's start now. So what we can observe is here you have two groups. One is Z2, and here there is another group under multiplication. So this is a group under addition. But what we can observe is although the groups looks different, but they have the same structure. So what actually happens here is you're changing the name of 0 as 1. This one you are kind of rename label as -1, and the operation instead of this symbol you are using this symbol. So other than the symbols are different, the structure of the group is the same. So that was kind of captured by the isomorphism. Okay. So this bijection, so we say two groups are isomorphism if there's a bijection, if the phi is a bijection and the homomorphism property is satisfied, right? So the bijection kind of tells you the relabeling. So if I have a element here G in this group, let's say it has a name G. Suppose if it goes to another group, so the same element might have a different name. Let's say that name I'm calling it phi of G. Okay. So in this case, if you look here, this 0 here, in this group I'm calling it as 0, but in this group I'm calling it as 1. But the object is kind of the same. Okay. So isomorphism is a way to capture this. Okay. So let's do some properties of isomorphism. So suppose if you have a isomorphism from G to H, then there are certain properties which are true. For example, if G is abelian, then H is also abelian. So the size of the G is same as the size of the H. Okay, why is this is true? This is because phi is a bijection, right? So phi is a bijection means the size are same. Okay. And there are other properties. If you take element here, G here, the order of the element is same as after you go to here, get the phi of G and take the order. Okay, so the order of G and the order of phi of G are same. And this is true for every G in G. Okay, and also the phi inverse. So since it is a bijection, right? Phi is a bijection. You can look at the phi inverse, which is a map from H to G, right? So what happens is the phi inverse is also an isomorphism. If phi is an isomorphism, then phi inverse is also an isomorphism. Okay, so I just want to make a small remark here. So in group theory, in order to do something like this, let's say some isomorphism, it is enough to say this one enough. Okay, so basically what you have to say is you have bijection and this property is satisfied. Okay, but if you want to go for let's say topological space, etc., what happens is this will not be true for a topological space. So in topological space, there is an equivalence called homeomorphism. We will say when two topological spaces are equivalent. But the problem there is, in general, it need not to be true. Okay. So there is a remark I want to make that this is true for group if let's say phi is isomorphism, the inverse is also isomorphism, but in general it is not true. For example, for topological space, this is not true. I mean, if you know what is a topological space, then it's just a remark I want to say. If you don't know, you don't have to worry about it. Okay. So in that sense, it is actually an interesting property for group. So once you prove that phi is isomorphism, the inverse by itself became isomorphism. In general, that is not true. For example, if you have a so this is what I want to say. Suppose if you have two metric spaces, if you know what is a metric space, okay, and here is a, let's say some function, okay, let's say the function is bijection and let's say continuous, okay. So then what we know is the inverse image exists, the inverse function exists, but in general this inverse function need not to be continuous. So, but in our case, if you look, this property is satisfied. Uh, for a group, this property is satisfied, but the inverse also satisfies this property. Okay. Okay, so this is one of the remarks that I just want to make. And if you look at the center of this group, the center of this group, if you want to look, that is basically you take the center of G here and look at its image. Okay, and that will be the center of H. And if you want to look at the commutator of this, so I think I might have defined the commutator. So commutator of HH. Anyway, in this particular course, we will not do much about commutators, but it's, so anyway, it's one of the very important objects. So I just want to remark it. This is basically nothing but the subgroup generated by HK, H inverse, K inverse. Okay, where H and K are element of H. So the subgroup generated by that is called the commutator subgroup. So if you have a two group which are isomorphic, then their commutators are isomorphic. Not same, but isomorphic. So here also I want to put a okay. Here it is equal, but here it is isomorphic. Okay, and we can also if there is a power n, you can bring it outside. So you keep using the homomorphism property again and again by index, and you can prove this. Okay. And probably the another property is a phi of G inverse. If you have the inverse, you can take it outside. Okay, so you can write it as phi of G whole inverse. Okay, the thing is, I'm not going to prove it because most of these properties are easy, so you can directly prove it. You just need to use this particular fact, okay, and most of the properties will come follows very quickly. So I'm not going to use that, but at least if you try to prove this few ones, I will just mention. If you want to prove, at least try to prove this one. Maybe just a few things you can try. Okay. So these three are probably interesting ones, and maybe you can try it as exercise. So if you want me to solve something, you can let me know. I can solve a few of this, but since these are like very trivial ones, I'm not doing it. So for example, few of this we have already done. For example, this we have already done because there's a bijection. And this also just use the index and it will come. But anyway, keep it as exercise. But we will do the interesting one later now. Okay, so let's start with this problem. So now let's move on to something interesting. So suppose if G is a group here, okay, and by automorphism of G, the set is basically the set of all isomorphism from G to G. Okay, so you collect all the isomorphism from a group to itself, and that set is called automorphism. Okay. So basically, if you look at automorphism of G, this is nothing but phi, okay, where phi is G to G is isomorphism. So basically, you collect all the isomorphism. Now, what happens is this is a group. So this automorphism will become a group under functional composition. Okay. So you start with the G and you collect all the automorphism, and the automorphism became group itself. Okay. So this is the first problem that we want to try to prove. So let's start to prove it one by one. So the first property we want to prove is that closure, right? So let's prove the closure. See, you see here, the operation is functional composition. Okay. So let's take two element f and g belongs to automorphism of G. Okay. So what does it means? So f is a isomorphism and G is also isomorphism. Okay. So and how you do the functional composition? So the functional composition is basically I'm looking at f compose G, right? So the claim is the following. The claim is f compose G. This belongs to automorphism. So basically that is same as saying f compose G is isomorphism. Okay. So let's prove it. So what is a f compose G? So you have a G. Okay. So you have map here G, sorry, you have map here G and you have F here. Okay. So this is how you define the F compose G, right? So we want to prove that this is a isomorphism. Okay. So in order to prove the isomorphism, we have to prove two property, right? First one is what? Um, F compose G is a bijection. See, this is true. This is obvious, right? Because F1G is a bijection, so F compose G is a bijection. So this is a standard set theoretic property. So this is clear. So now let's prove that this is a homomorphism. So this might take some work. Let's prove. So what you want to prove? F compose G of, okay, I shouldn't have used F1G, but anyway. So let me take two elements X and Y here. Okay. So where let X comma Y belongs to G. I shouldn't have used the symbol G, but anyway. So let's look at F compose G of XY. Okay, maybe I will just change the symbol because it is not good. Because usually we use the G for a group element, so I don't want to. Yeah, I don't want to change that. So let's take two element. Let's say G comma H belongs to G. Okay. So what I want to look is basically phi compose psi of GH, right? Okay, so what is phi compose psi of GH? So how the composition works? You take phi of psi of GH, right? Now use see the psi is a isomorphism. So let's first use this. What you get is phi of psi of G times psi of H. Okay. Now we will split here. So phi is a homomorphism. Sorry, phi is isomorphism. And you see this is one element, this is one element. Okay. So now if you observe here, what is this? This is nothing but phi compose psi of G, and the other one is phi compose psi of H. Okay. So what we have proved is phi compose psi of GH is phi compose G of G and the phi compose psi of H. So that tells you that phi is a homomorphism. Sorry, phi compose psi is isomorphism. So that means the closure property is done. So closure means you take two elements and then you have to multiply and they say that element also belongs to the same set. So closure is done. Okay. Let's look at the associativity. So, okay, associativity is also clear. So why associativity is clear? Because if you have a function composition, the composition is always associative. So it does not matter if it's a homomorphism or not. In general, if you have let's say three function, let's say f from some x to y, and g from let's say some y to z, and let's say h from some z to r or some set. Okay, so it is always true that f compose and g. Okay, I need to write it properly. So f compose g compose h. So whichever the way you want to compose it, it is always true. Okay. So if you want, you can keep it as exercise. So it is true irrespective of whether it is a group homomorphism or not. So that doesn't matter. As a set function, the associativity always holds. Okay. So here also in this group also, because the operation is composition, uh, the associativity holds. Okay, let's look at the identity. What is identity? Okay, if you want, I will just prove it here. Uh, anyway, because I don't want to leave it here. So let's start by saying it. Okay. So what is a? Let's look at this element. What is that H compose and G compose F? So F is a map from X to Y, and Y to Z there is a map. This is F. This is G. So this is H. So this particular function. So you usually write like this. If you have in this direction, the map usually goes in this direction. So that means this composition is a map from X to S, right? So let's start with H compose G compose F of X. Okay, what is this? This is nothing but H compose G of F of X, right? Okay, now what is this? This is nothing but uh, okay. So how the H compose G acts on some F of X? It acts on F of X as H of G. So you see it as a single element. So how the composition acts on the single element? So whatever the element is, you have to write like this, right? Okay. Now if you look just the whatever it is inside, what is that? That is nothing but H compose. Sorry, let's leave it. It's H of. So just look at what is inside. Okay. So this is basically F compose G. Sorry, not F compose G. This is G compose F. F of X. Okay. So this is one function. This is another function. So now how the composition goes? It goes like H of G compose F of X. So we just proved it. We proved it. This is same as this. Okay. So there is not much to prove. Okay. So associativity also we proved it. And anyway, this is true for all the X belongs to X. So in general, you put all the X, Y, Z and all of this as a G, G, G. So we get our associativity that is needed. Okay. So in particular, this associativity does not require any group condition. As long as it's a map, the associativity is clear. As long as you have set map, the associativity always there. Okay. So let's prove the identity. So what is the identity? Identity is nothing but so I write it as a capital I. This is a map from G to G. So what it does, it takes the G to G itself. So this is my, I'm claiming this is my identity. I haven't proved it yet, but so I'm claiming this identity. Okay. In order to say that, first I have to show that this I actually belongs to automorphism. So basically this I is the isomorphism, I want to say. Once I said that, then we prove that this is a identity. Okay. So clearly this I is a bijection, right? So what we want to prove again is I of GH. We want to prove, so what is I of GH? This is GH. So but G I can write it as I of G, and H also I can write it as I of H. So that's all, right? So this is the first property bijection. Anyway, this is just identity map. That is always a bijection. The second property is also obvious. Okay. So what we proved is I belongs to automorphism. Now let's look at, let's say suppose F belongs to automorphism. What we are claiming is F compose identity is nothing but F. Okay. So this is the claim. So let's start with that. What is F compose identity of G? Okay. This is nothing but F of identity of G. But identity of G is just G. So this is equal to F of G. Okay. So what we have proved here is F compose identity. So okay, I start with the G in G, and then I have proved that F compose I of G is nothing but F of G. So that means F compose identity is nothing but F. Okay, so this proves that this identity I defined here, the identity map, is the identity of your automorphism. Okay, now I want to prove the inverse. Okay, so let's start with the F belongs to uh, automorphism of G. So what we know is we know that F inverse basically is a map from G to G. We know that this map exists, right? So, but what we have to show is this map is also an isomorphism. So we claim this is the inverse of F. Okay. So this is the claim. I haven't proved it yet. So let's prove it. So basically, this was the exercise that I have mentioned here. So this is the exercise that I have mentioned here. But anyway, let's prove it. But here I'm using the same G to G, but whatever we will prove will holds for in general. The same proof, you just change the symbols. Okay, so anyway, since we need it, let's prove it here itself. Okay, so what I want to prove? I want to prove F inverse of GH is nothing but F inverse of G times F inverse of H. So this is what we want to prove, right? So, okay, so what is F inverse of GH? So let's say F inverse of GH is some X. Okay, so what is the property we have about that particular X? What we have is say some X, okay, and it belongs to G. If you want, I can draw a map here just to visualize. So here you have F here. Let's say we have 3 points, G, H, and GH. Okay. So this is F of G, and this is F of H, and this is F of GH. Okay. So what the property we have is if I apply F to it, if you look at this, what you get is F of X. So this kind of cancel out. So what you have is GH is equal to F of X. Okay. So probably I need to change this symbols here. Just the name I will change here. So let's say this is GH, and so this is EX. Okay. So this X is nothing but GH, or maybe I will call it as EZ. Just sorry about changing the symbol in between. Okay. Okay, we have this one. So, but let's look at the other one. What we have to prove is so F inverse of G, F inverse of H. Okay. So what we do is the following. Okay. Here you have a G, here you have H. Since my map F is a bijection, so there exists X, there exists a Y, and there exists a Z. such that this x goes to G, y goes to H, and Z goes to GH, right? Why this is true? Because F is a bijection. Okay. So now what I am going to say is, suppose this is Z, I'm going to say this Z is equal to nothing but x comma y. Okay. So let's apply it here. This gives you GH. Okay, maybe I have to write it properly. Okay, maybe I don't need it for now. I will just come back to it later. Let's call the F inverse of G as x and F inverse of H as y. So what we want to prove is Z uh, is equal to x, y. So this is what we want to prove. So here you can see, this is what I'm claiming. So this is my claim. So this is same as telling Z equal to xy, right? Okay, now apply that function here. So how do you prove it? What you do is you take the Z, which is nothing but F inverse of GH, and you apply F to it. Okay, so this is nothing but GH. Okay, now you take the other element, F inverse of G and F inverse of H. Now you apply F to it. Okay, now since F is a homomorphism, it kind of splits. So let's split it and write. This is F of F inverse of G and F of F inverse of H. Okay, and this will be GH again. So basically what we did is we took this element and this element. So this is both, we want to prove this is our claim. But what we do is let's apply F on both sides. Okay. So when you apply F on both sides, what you get is the following. First thing, if you apply F, you will get GH. And the second one also, if you apply F, this kind of splits. So I have something like this. Okay. So because F is isomorphism, it splits. And this inverses I can cancel out. So what remains is GH. So what happens here is there is a two element. Okay. Two element in here. So one is this element and another is this element. And both of them maps to same GH. Okay. But what we know is F is an injective map, right? So under F, there are two elements which goes to the same GH. But what we know is, but F is nothing. F is an injective. Okay. So F is injective map means what? If you take two elements, they have to go to two different element. If you take, they have to go to different image. But these two elements are going to the same image, so they cannot be different. If they're different, the images has to be different. But since they're going to same image, the elements has to be the same. Okay, so that's what we are going to write. So that tells you this is equal to F inverse GH inverse of H. Okay, so that's all. We got it. So basically what we did is maybe I don't even need this. So I will just erase it. So what we did is you take this and you take this element and apply F on both sides. What you can see is both will become GH. Okay. So there are two elements here, this one and this one. Both goes to GH. So that means these elements has to be same. Why? Because this F is an injective map. Since F is a 1-1 map, if they are different element, then the image has to be different. But you see the image after applying F, the image is basically the same. Since the image is same, the elements has to be same. Okay. And that's kind of prove the statement. Okay, so this tells you that F inverse is also injective. Sorry, F inverse is also isomorphism. Okay, and clearly you can check that F compose and F inverse is nothing but identity. Okay, so this is just a set theory result. So what we have shown is, if you look at this automorphism, all the four properties are satisfied. Okay, so this automorphism is a group under composition. It's one of the very important group. So studying the automorphism of group is actually very important. So if you know some vector spaces and all, the matrices are basically the automorphisms. That's why the matrices is important. So you might have seen the GLN, etc., right? So GLN is basically automorphism of the vector space. Okay, if you know what is a vector space. So any automorphism is actually important object to study. So one of the reason the matrices are a very important object, it's basically they captures the automorphisms. But anyway, let's move on to another question here. So this is also a little bit interesting. So the question says the following: let's G be any group. We will prove that the map G from going from G to itself, defining by G goes to G inverse. This is a homomorphism if and only if G is abelian. Okay. So take the G to G inverse. This map is a homomorphism if and only if G is abelian. That is what we try to prove. Okay, so here you want to prove the if and only if statement. So let's prove both direction. Okay, first we'll prove this direction, and then we will prove the other direction. So here we assume that this map is a homomorphism. So let me call this map as phi from G to G, going G to G inverse. Let's assume it's a homomorphism. Okay. So that means what? If I take phi of GH, so what is phi of GH? This is a GH inverse, right? Okay. So this has to be equal to phi of G, phi of H. But what is phi of G? This is G inverse, and phi of H is H inverse. Okay. So basically what we have is GH inverse is equal to G inverse, H inverse. Okay. But we know what is GH inverse is, right? GH inverse is nothing but H inverse, G inverse. Okay. This is the Susak's lemma that I'm using here. So we have done it in the first class. You can observe that if you have two elements in the inverse is nothing but you write this element here. So basically you cross it. So the H has to come next and G has to come first, and then you take the inverses like this. And this is equal to G inverse, H inverse. Okay. So this is true because this equality is true because we are assuming this is a homomorphism. In general, this need not to be true. Okay, now what we can do? So what we do here is let's multiply this side by G and then H. Okay, so let's multiply this side by GH. So what you get? You get H inverse G inverse GH is equal to G inverse H inverse GH. Okay, so if you look here, this cancel out, this to cancel out, and this to cancel out. So totally this is identity. This is equal to G inverse H inverse GH. Okay. So if you know the commutators, you can directly conclude from here the group commutes. But anyway, we'll do one more step, then it will be more clear. So let's multiply this side by GH, sir, HG. Let's multiply here. So if you multiply, what you get? HG equal to HG, G inverse, H inverse, GH. Okay. So if you look here, this will go out and this will cancel out. So what remains is GH. Okay. So basically we proved that HG equal to GH. And this is true for all GH. Belongs to G. This is true. So this tells you that the group is abelian. Okay, so elements, every element commutes with each other. So the group is abelian. Okay. So let's go the other direction. Here you assume that the group G is abelian, and then we want to prove that this is the uh, inverse, right? So how do you go here? We do the same thing again. So if you want to prove this other direction, what you do is, so basically whatever you did here, just reverse here. Okay. So anyway, I will just write it once, but the idea is basically you just go up. I mean, just reverse it. So abelian means Hg equal to Gh. Okay. So, but now what I want to prove here, I want to prove this is the homomorphism, right? Okay, probably we can prove this is homomorphism directly. So this is known. So what we want is phi of GH is equal to phi of G, phi of H. Okay, so this is the claim. Okay, what is phi of GH? This is GH inverse. Okay, so let's start with the phi of GH then. So this is GH inverse, which is equal to H inverse G inverse. Okay, but since my group is abelian, I can commute these two elements, right? So I can commute, so I can write it as G inverse H inverse. Okay, but what is G inverse? This is phi of G. What is H inverse? This is phi of H. So what we have proved is phi of GH is phi of G phi of H. So that means this map is a homomorphism. Okay. Okay, so this is one such thing. There is another statement like this. So the map from G to itself defined by G going to G square. Okay, so this is a homomorphism if and only if G is abelian. Okay, here we are having G inverse, and here there's another map. This is G square also. Okay. Okay, so let's prove this also. So the problem is what? Phi from G to G. It takes G to G square. So this is a homomorphism if and only if G is abelian. So let's prove it also the same way. So first let's prove this direction, and then we'll prove the other direction. So in this case, let's assume that this map is a homomorphism, and let's try to prove G is abelian. Okay. So here the real problem is if you want to say G is abelian, what I want to say GH equal to HG, right? So this is my claim. But the homomorphism has only one element. So the idea is how to bring the H here. Okay. So that was the actual problem here. Right. Okay. So let's prove it anyway. Let's take two element G and H belongs to G. So let's use the property that it's a homomorphism. So what I have is phi of GH is nothing but phi of G, phi of H. So what is phi of GH? It is GH square. This is equal to G square H square. Okay. So what is GH square? This is GH, and this is equal to G square. So G square is what? GG, HH. Okay. So let's cancel out this. By cancelling, I mean multiply by H inverse, and that will cancel out. So we can cancel this two element, and we can cancel this two element. So what remains is Hg equal to Gh. Okay. So that means G is abelian. That's all. So now how do you prove the other way around? Other way around is again you just go directly above. It's the same idea. So let's assume G is abelian. So let's assume this. And what we want to prove is so we claim phi is a homomorphism. So phi is a homomorphism means what I want to prove. Look here, what I want to prove is the following. So basically, this step is what I want to prove. So let's start with phi of GH. Okay, this is nothing but GH the whole square. Okay, so what is GH the whole square? And this is GH. But you see, my group is abelian group, right? So I can commute these two elements. This H and G I can commute. And this became GG, H. So basically this particular element I am commuting. So this is G square H square. This is phi of G, phi of H. Phi is okay. Okay, anyway, we proved it here, but probably in the proof we might have lose the intuition what is actually happening. So if you look here, what is actually happening is the following. You see here, in general, see this guy is nothing but this one, right? GH the square. So this is GH. But in general, you cannot commute it. Okay, if you have two elements, in general you cannot commute it. But if you have a abelian group, you can commute it. Okay. So here also the only property you need is basically you need to just commute. Whether you can commute or not is the problem. Okay. In order to prove this G square is homomorphism or not, uh, what is actually you need is whether you can commute it. If you can commute, if these two elements you can commute like this, then it's a homomorphism. But in general, you cannot commute it. So that is the problem. Here, the inverse also the same problem comes, right? I will show it here. So here you observe here also. So GH inverse is basically H inverse G inverse. But the question is whether you can write it as G inverse H inverse. In general, you cannot. But if you have abelian group, you can write it, and hence it became a homomorphism. Okay. So basically, this is the problem of commutativity, and in some sense, it captures abelian. So if you want to say a group is abelian, it is enough to prove this map is a homomorphism. Okay. But anyway, in other way, I can say another thing also. In a abelian group, if you take GH power n, this is equal to G power n H power n. Okay. So this is if G is abelian, then this statement is true. Okay. So how do you prove it? We have proved for the square, we have proved n equal to 2, we have proved just now. The homomorphism basically tells exactly the same. But for n also you can prove. In fact, the square, if you replace by n, where n belongs to natural number, in the square, instead of the square, if you put n, the statement still holds. But the problem is, okay, anyway, since I mentioned it, let me mention it clearly. So if G is abelian, so what we have is this map always, so G maps to G power n is a homomorphism. So this is always true. Okay. But in general, whether the converse part need not to be always true. Okay. So the converse is true if the n equal to 2, the converse is true. Otherwise, the converse always need not to be true. For example, if you want a counter example, so I will write here converse is not true. So if you want a count example, take G as Z3 to Z3. Okay, and consider this map. So what will be this map? This basically means you take X and maps to 3X, right? So 3X is always 0. So this is a trivial map. Trivial map is always a homomorphism. Okay, anyway, but this group is also abelian. Okay, that does not tell us anything. Okay, then the other example that you can take might be, I think, quaternion or something others. But anyway, in general, the converse may not be true. But this statement is always true. This direction is always true. Maybe you can try to think of the converse. So I don't able to see any easier group that does not satisfy the property. But there may be other groups. Okay, anyway, let's move on to our next problem. So anyway, remember this. This is true if you have a abelian group. If you don't have a abelian group, this statement is not true. You cannot always write gh power n as g power n h power n. In fact, what happens is when you write it, there are some other additional term comes here. So basically, this is gh power n choose 2 etc. comes, and that is why these commutators are important. Because commutators are important because they appears. So when you want to change the elements from here to here, you cannot always do, but there is a abstraction comes in terms of commutators. Okay, but anyway, the commutators we are not going to do much, but it is there. So basically, commutator GH is nothing but GH G inverse H inverse. Okay, so this kind of comes here. Yeah, but that is just a remark, but we don't need it. So let's move on to next question. So this is again one of the important question, and it is actually useful also. So probably after proving this, I will tell some little bit of story about this. But let's try to prove it. So the question says prove that if G by Z is cyclic, then G is abelian. Okay. So you know what is G by Z, right? So the element of G by Z is what? The element looks like this. What is sorry, not G, this, yeah, element looks like this. This is nothing but G comma Z, where Z belongs to Z. Okay, by the way, I'm not sure if I mentioned what is Z. Z is basically center here. Z is basically center. Okay. So center of G is a set of all elements that commutes with every other elements. So what we have is, so if you look at G by Z, the elements are GZ, and how the multiplication looks like, if you have two element, GZ times HZ. Okay, maybe I don't want to put a dot here. Times HZ. This is nothing but GHZ. Okay, so this is how the multiplication looks like. Okay, so the question says if GZ is a cyclic, then G is abelian. So let's prove it. Okay, so let's say GZ is a cyclic. Okay, so let's see what happens here. I have a G and I have homomorphism here, G to G by Z. Okay, so what is the homomorphism? You take G to GZ. What I know here is this group is a cyclic. Okay, and what we are trying to say is this is abelian. So let's prove it here. So let's say this is cyclic, right? So let's say G by Z is generated by AZ. Okay. So since it is cyclic, we can assume that G by Z is generated by AZ. comma A is some element of G. So for some element A of G, Gz is generated by Az. Okay. So suppose if you look at G, so G is here. So let's move the G to here. Okay. So now what happens? What happens to this Gz? Okay. Anyway, see, this is not a correct notation. Okay. When you write something like this means integers. Okay. So center is usually denoted by center of G. Sometimes people just write Z. Okay. So you should not put like this. Okay. So this here, this is the element here, right? So Gz is the element here. But I know that Gz is cyclic, so it is generated by A power Az. So what happens then? Gz is basically A power nz for some n belongs to n. Because this is cyclic group, right? Cyclic group is all the powers only comes. Okay, and we know how the multiplication looks like, right? Az times Az is nothing but A square z. Okay. Okay. Now what happens is Gz is this element. As a set, these are same, right? Now this G belongs to this set. Okay. So that means G also belongs to A power nz, right? So how the A power nz looks like? A power nz looks like A power n small z, so that this small z contained in your center. So that's how all the elements looks like. Now G is one such element. So what happens is there exists Z belongs to Z, such that this G is equal to A power n Z. Okay. Okay. So this much we have. So what we have shown so far, I will tell the summary. What we have shown so far, what we have seen so far, is assuming G by Z is a cyclic. What we can say is any element of G has to have this particular form. Okay. And this n can be different depending on the G. This n will be different. This Z will be different. Okay. Thus, if you take a two element G comma H belongs to G, then G should be looks like A power n the small z, and H should be looks like A power m, let's say Z1. Okay. Where this Z belongs to center, this Z1 also belongs to center. Okay. Now what we want to prove is we want to prove G is abelian, right? So that means we want to consider GH, and I want to say it is equal to HG. So we are claiming this is equal to HG. So this is the claim, right? So let's start with the GH. So what is GH? This is A power n Z, and what is H? This is A power m Z1. Okay, so this is good. Now what we want is we want H, we want HG, right? So let's just move these things around here. That is what we are going to do. Okay, let's move it one by one. Okay, so what we are going to do, first we will move it here. Okay, this is equal to A power n, A power m, Z, Z1. Okay, why this movement is possible? This movement is possible because this element is in the center. So that means it commutes with every other element, right? This I can always commutes because this Z is in the center. Okay. Okay. So now what we can do? So now we moved one element. We moved one step. So we can move this also, right? Because A and A always commutes. So any power of n and any power of m. Sorry, these two elements are basically some power of A, right? So this you can write it as, if you want, you can write it as A plus m plus n. That one. But this is nothing but A power m plus n. Okay. I mean, this you can write it down like that, but the idea is not this. The idea is These are actually power of the same element. So a power n is what? A times a times a times a, etc. Right? So basically a commutes with a. That is what we are going to do. A commutes with itself, and hence any power also commutes with itself. Okay. So if you want to, write it regularly, you can write it like that. But the idea is you can commute it. Okay. So that's that one. Now what you do is see, I want h g, right? So I want this is equal to h g. That is what I want to prove later. So just keep that in mind. So what that means, I want to move this guy over to here. So far I moved this one, but see, look, this z1 is in the center again. So I can commute with each of that. So I can move the z1 here. Okay. Okay. Now you just change the bracket here. What this is nothing but this is h, and this one is g. This one is h. So what we have proved is we have proved GH is equal to HG. Okay. So because these elements come, this A power m commute with A power n, and then this element in the center commutes with everything. So we can move it according to our wish. So basically, these elements commutes with each other, and let's just move it around, and then we have proved it. Okay. So let me tell you a little bit more. So what we have proved is the following. If G by Z is a cyclic, then G is abelian. This is what we have proved, right? So let's keep that in mind, and I will give a little bit of remark. So what we have proved is G by Z is a cyclic, right? G by Z is cyclic, implies G is abelian. Okay. Suppose G is so this means G is abelian, right? So G is abelian means what? G is abelian means the center of G is equal to G. So this is one of the exercises that gives in the classroom, and we have proved it. Okay. So this is same. So G is abelian is same as saying center of G is equal to G. So what does that tells you about G by Z? If you look at G by Z, see the center of G is basically G itself. So if you look at G by Z, G by Z is basically what? This is just a identity, right? Just one Z. Just a single element will be there. So not one Z, one Z. Yeah. So there's only single element. So this group is basically isomorphic to just identity group. Okay. So basically what we have seen here is if G by Z is a cyclic, then G by Z is equal to 1. That is what actually it says. Although it says abelian, and then once you do a little bit more, this is what it says. So if you want to write it other way around, little bit differently, what it says is only cyclic group, let me call it as let's say K, which can be written as G by center of G for some G is identity. So basically what, okay, I'll just repeat it. So the only cyclic group, okay, which you can write as G by center of G. So if suppose if you want to write this K as G by center of G for some other G, okay, the only possible such a cyclic group is identity. So that is what this statement tells you. Okay. So in general, you cannot write any other cyclic group as G by center of G. Okay. So there is one question comes here. So there is a natural question comes here. Okay. So what other groups H can be written as G by center of G? Okay. So this is one of the natural question that comes. And so this is known for abelian groups. For abelian groups, we can say what are the groups that can be written as a G base center of G for some other group. But in general, we don't know. So the answer, okay, we don't know. For abelian groups, it is kind of known. At least finite abelian groups which are finite, we know. But other than abelian group, for non-abelian group, we don't actually know. Okay. So that's just a remark I want to say. Any group H for which you can return as like this, these groups are called the capable groups. Okay. And in fact, it's an open problem. So the open problem is what group you can write it as G by Z for some other G. Okay. So this statement kind of tells you other than the trivial group, no other cyclic group can be written as a G by Z. So the question is, okay, cyclic group is done. In fact, abelian group is also known. But is there any other group? What about the other groups which are not abelian? Okay. So although see, if you look here, this is a very trivial looking statement, right? The statement is easily I can stay as once you know what is a quotient group, I can state the question. But it's kind of just open for a century almost, and yeah, in general, it's very hard. Okay. So is there a criterion? Can you say a criterion? This a group is capable if and only if some statement. Well, we don't know. Okay. Anyway, this is just a remark I want to say. So in group theory, the questions may be very easy to state, but the proof need not to be easy. So, but we know a lot of things, but there are a lot of things we still don't know. If you look here, these are all very easy looking statement, but still we don't know. Okay. Anyway, let's move on to a different one. So what we have done so far is we have done about the isomorphism theorems and homomorphisms, etc. So now let's move on to the Lagrange theorem. Okay. So let's start this is a section from Lagrange theorem. Okay, so here we will do some interesting questions. Okay, probably I will just show it out. Maybe we'll come back and do it. For example, this is one of the questions we'll do here. So the question is determine the last two digit of this number. So this is a big number, right? 3 power 100. This is a big number. So the question is, what is the last two digit of this? In general, doing something like this is not easy, right? Because you cannot never multiply it. If you multiply it and write it down, it's a huge number. But we can use group theory, and then we can just compute the last two digit. So probably this is one of the problem that I want to do. But let's go a little bit, do some other problems, and then come back. Okay, so let's use the Lagrange theorem. The question says the following. Let G be a group. Which of the following are permissible order for subgroup of group of order 10? So basically you have group of order 10. So what are the possible orders for the subgroup? That is a question. So the question is, the orders is 1, 2, 5, 7, 9, 15, 16, 240. So you can answer it actually. If you want, you can just type in the chat box.
1, 2, 5, 15,
Okay,
and 60.
And 60. Okay, let's check it once again. So let's look at 120. This is equal to 2 times 60, which is equal to 2 times 2 times 2 times 3 and 5. Okay. So Lagrange theorem says the following. Oh, okay, you are right. So these are the answers. So you are right. So what the Lagrange theorem says, it says the following. Suppose you have a H which is a subgroup of G. Then what Lagrange theorem says is the cardinality of H divides cardinality of G. Assume these are finite groups. Okay, these are finite groups. Okay. If it is not finite, also Lagrange theorem says something, but it does not tell anything about the order. You can say something else. So the order is interesting. See, basically, Lagrange theorem is interesting if your group is a finite group. Then it tells a lot of information. Okay. So the permissible order are the things which divides 120, right? And these are the only things that divide 120. So for example, 7 does not divide 120, so you can see here. 9 also does not divide because there is only one factor of 3. 240 is even bigger than 120, so it does not divide 120. So these are the correct options. Okay. So let's move on to next one. So here is the another question. It says let's say your G is of order PQ. Okay, where this P and Q are a prime, and it does not need to be distinct. Okay, so the question says that then either G is abelian or center of G is 1. So right now we are not classifying it, but it kind of tells you whether this statement is true or the other statement is true. So basically it says G is abelian or center of G is 1. So for example, can you say any group of order PQ, like some group that you know? For example, you look at S3. Okay, this is 6, right? Which is 3 times 2. Okay, and you see the S3 is not abelian, so we can directly say from here center of S3 is nothing but 1. So these kind of statements are always kind of useful. But anyway, later once you're done, probably towards the end of the course, you can actually classify these groups. A group of order PQ, you can just say these are all the groups. In general, this is not easy task. If you given a number, what are all the groups? Okay, this is not an easy task, but for PQ, you can actually classify it. Anyway, I gave the spoiler, but these are nice groups. So this is a nice order. This you can kind of classify. You can say, okay, these are all the groups. Anyway, let's go quickly. So we have to prove one of the following, right? So how do you prove that? So far what we have done here, most of them are just routine. But if you look here, this is something interesting. So probably will give you 2 minutes to think maybe. Just think for some time and probably you can tell me. Yeah, by the way, that's a hint here. But the hint, yeah, I didn't write here, but the hint basically says this one. This you can use it. So that's the hint. Okay. So what you can say is G by Z is cyclic, then G is abelian. Okay. So that is the hint. Okay. So basically, what you want to do is you want to work with the center of G. So what we can look at, let's look at what are the possible order for center of G. By Lagrange theorem, the possible orders are 1, P, Q, and PQ. So these are the possible orders. Why? By Lagrange theorem. So, but the statement kind of tells you that it is either 1 or it is PQ. So basically, what it says, center is abelian. That means what? Center of G is equal to G, right? So the statement says the size is either 1 or PQ. So that is what it tells. So it kind of tells you this P and Q is not possible. Okay, let's assume. Let's go by proof by contradiction. Let's assume. Okay, so the see, it doesn't matter whether you take P here or Q here. There is kind of symmetry here. as long you can, it's enough to prove one of them. The other proof also goes exactly the same. Okay. So let's take a center is actually P, and we'll get a contradiction. Okay. So how do you get a contradiction? So let's look at G by center of G. Okay. So what is the cardinality of this? Cardinality of this is nothing but PQ by Q. Sorry, PQ by P. Again, this is also follows from Lagrange theorem, right? Why? This is nothing but the index here, G index center of G. Okay. So order of this is basically G index this. But the Lagrange theorem says this is nothing but the index, order of the index is nothing but order of G by order of H. Okay. Sorry, not order of H, order of G by order of center of G. Okay, so basically you can just write the both orders and you can divide it. Okay, that's all. So we can divide this order is Q. Okay. So what happens is we have G by center of G. This order is Q. From here, what we can say? If we have a prime power order, such a groups are cyclic actually. Okay. Maybe if you don't know, probably I'll prove the statement, but let's proceed here. Okay. So thus, G by center is cyclic. Okay. If G by center is cyclic, what we know? So this implies G is abelian. And that's all. Okay. So if it is other than 1, then these are the only 3 possibility. Whichever the one you assume, you kind of end up getting it's abelian. Okay. Oh, anyway, by the way, I haven't tell you what is the contradiction. If it is abelian, that means center of G is basically equal to G, but that implies the center of G, the size is actually PQ. This is a contradiction. Okay, so this is not possible. Center of G is equal to P is not possible. Q is also similarly, you can prove Q is also not possible. So the only thing is either this or this. But anyway, in order to do that, what we have to prove is that this statement is left. So let's prove that also. So basically, what is the, so there is a lemma here. Let me write it down. If cardinality of G is some P, where P is a prime, then G is cyclic. Okay. Okay, so how do you prove it? So G cyclic means what I want to say. I want to say G is generated by this for some G is what I want to prove, right? So this is my claim. Okay, but how do you prove it? Let's take G which is not equal to 1. Okay. So let's take a non-trivial G. Okay. And let's consider the cyclic subgroup generated by G. Let's call this as H. Okay. So what we know is by Lagrange theorem, we know this cardinality of H divides cardinality of G. So that implies this cardinality of H is either 1 or a P. Okay. But you can see here, cardinality of H is not equal to 1. Why? Because 1 belongs to H as well as G belongs to H. And they are not equal, right? Because H is a subgroup. So these two belongs to H, but they are not equal also. So that means the cardinality of H is already greater than or equal to 2. Okay. So the only possibility is P. That's all. So that tells you the cardinality of G is G. Okay. So that tells you what? So basically this H is a subgroup of G, but they have same cardinality. That means they are same, right? See, you can clearly see here how this Lagrange theorem is useful. Okay, see here we are using the Lagrange theorem. Here we are using the Lagrange theorem, and only we are proving it here. So in that sense, Lagrange theorem is like very useful. Okay. So this we have done here. So this question we have done. Let's move on to the next question. But anyway, if you want, you can just recall the statement. So sometimes it's a good idea to know the statements. So if you have a group of order PQ, then what you know is it's either abelian or center is 1. It's either abelian or the center is 1. Okay, so let's move on to another question here. If we have two groups H and K, which are finite subgroup of G, and its orders are relatively prime. Okay, so relatively prime means the GCD of the kernelities are actually equal to 1. Okay, so the claim is the intersection is empty. Okay, so how do you prove it? So again, use the Lagrange theorem. That's all. So let's say okay. So what we can observe is this intersection is first a subgroup of H, and also it is a subgroup of K, right? Okay. So let's use the Lagrange theorem in both cases. Okay. Then what happens by Lagrange theorem? What happens is we will write here. Okay. So this size divides H, and also this size divides K, right? This divides the size of K. Okay. So basically, so this is a divisor. The size of H intersection K is a divisor of size of H and the size of K. So in particular, what happens? This size divides the GCD because GCD is the greatest common divisor. It's the greatest among all the divisor, and this is one such divisor. So it divides this size, divides the GCD. But this is one actually. So that is a claim here. So that is the hypothesis. They are relatively prime. So this is one. Okay. So if that is 1, then what we can conclude here? So basically this number divides 1. So that means H intersection K. This size, see this size is at least 1, right? Because identity will be there. So this size is at least 1, but it divides 1 also. So this is equal to 1. Okay. So that's all what you want to do. So the size is 1. So what we have proved here is size is 1. What is that one element there? The one element is basically identity. Okay, so H intersection K sorry, is equal to 1. Okay, here we are using so many ones, but I think it is clear from the context when I write this one belongs to the center, but this one is basically identity. So one is identity of H and also K. Okay, so I mean there is a overload we are doing on this symbol, but it's kind of clear from the context. Okay, but this is like the symbol got overloaded with the different meanings, but from the context you try to understand what is the one means. Okay, so that's all. We just apply the Lagrange theorem and then we are done. That's all. Okay, let's move on to another question. So this question says that use this Lagrange theorem. So this is one of the famous theorem from number theory. It's called the Fermat-Little theorem. So what we are going to do, see, one can prove it directly in number theory, but we are going to use Lagrange theorem in this multiplicity group, and then we are going to prove the Fermat-Little theorem. So basically, the Fermat-Little theorem follows from just looking at the particular group. Okay. So if you just look at this particular group and then use the Lagrange theorem, you will get the Fermat-Little theorem. Okay, anyway, the Fermat-Little theorem says the following. If P is a prime, then A power P is congruent to A mod P. Okay, for all A in integer. Okay, if you don't know what is a model or what is a mod means, I'll just recall the mod. Okay, so we write A is congruent to B mod n if n divides B minus A or A minus B. Okay, so this is the formal statement, but what does it means is the following. So basically, if you take the A and then you divide by n. Okay, so what you get is take A and divide by n. Okay, so you get a quotient and a remainder, right? So I will call it so this is a quotient and this is the remainder. So you take A and divide by n. By dividing, you always get a quotient and a remainder. Similarly, B also gives a quotient and a remainder, right? So we say this A is congruent to B mod n if those two remainders are same. So this remainder and whatever the remainder that comes for B, if those remainders are same, then we called A is congruent to B mod n. So these two numbers are congruent if after multiplying, sorry, after dividing, the remainders for this and the remainder of this is same. Okay. So that you can write it in terms of this. Okay. Because when you subtract it, what happens is the remainder. See, so basically, what happens here? I will write here. So A is equal to Q1 n plus R1, right? And B equal to Q2 n plus R2. Okay. So this is a quotient and this is a remainder. And of course, we know that 0 is less than or equal to R1, R2 is less than n, strictly less than n. Okay, so the remainder is kind of less than the number n. Okay. But if you look at B minus A, okay, B minus A, then what happens is you have a Q1, sorry, Q2 minus Q1 times n plus R2 minus R1, right? If the remainders are same, then this kind of goes away, right? And if you look here, there is a n term here. This n will divide B minus A. Okay. So that is what we are trying to say. So basically, we say A is congruent to B mod n. If basically when you write like this, the remainders are the same. Okay. For example, let's take two numbers and probably will tell you what. For example, we do this one, modify, and let's say we take 3. Okay, so what are the numbers that is congruent to 3 modify? Okay, so 8 is congruent to 3 modify, because if you see 8 and 3 has leaves the same remainder when you divide. So if you divide 3 by 5, the remainder is 3. When you divide 8, the remainder is 3. So what is the other one? Uh, you can take maybe 13. Okay, you can take 18 and then 23. Okay, so these are all gives the same remainder. So this is congruent. And you see the modular arithmetic is actually it's a equivalence relation also. Okay, so you can write equivalence. A is related to B if and only if A is congruent to B mod n. Okay, so for some n, if you write like this is the equivalence relation. Okay, and using only this equivalence relation, we construct that Z mod n z, right? Okay. Okay, so this equivalence relation partisans, and then once you do that, you will get Z mod n z. Okay, now let's prove the theorem. So what we are going to do is we are going to use the Lagrange theorem in the multiplicity group Z mod Pz star, and then we will prove the Fermat-Last theorem. Okay, so the Fermat-Last theorem says if P is a prime, then A power P is congruent to A mod P. Okay, so that is what the Fermat-Last theorem, Fermat-Little theorem says. there's another theorem which is very popular. It's called the Fermat last theorem. Okay, not little theorem. And this theorem was kind of remain unsolved for more than 300 years. And I think in around 1995, Andrew Wiles solved it. But that was a different theorem. This is actually a small theorem. That's why it's called little theorem. Because last theorem is actually a big theorem, but this is a small theorem. Okay. So if you have any doubts regarding this, you can ask me now. Otherwise, I will assume that you understand it, and let's try to prove it. Okay. So I will assume that we understand what is the modular arithmetic. So let's try to prove the following. So what we want to prove is a power p is congruent to a mod p, right? Yeah. Okay. So this is what we want to prove. So, and the hint what you are telling is use the Lagrange theorem. Okay. Use the Lagrange theorem for the multiplicative group Z mod Pz. So what is the, look at this Z mod Pz star. Okay. So what is the order of this? So Z mod Pz star are invertible elements, right? Under multiplication, whatever the invertible elements, that is what we want to look at, right? So if you look at that, other than 0, so this is basically, this set is other than this 0 set, this has no inverse. Okay, sorry, 0 plus pz. So this has no inverse. Other than this, every other element has an inverse, right? So this cardinality is basically p minus 1. Okay. So maybe you might need to know a little bit of modular arithmetic to say that this is a group, but I think this we have done it, right? Yeah. So this is a order p minus 1. I think in the class it might have been done. If not, you let me know. We can discuss a little bit. Okay. So this order is a p minus 1. So if you take a element here a, so what does the Lagrange theorem says? So the Lagrange theorem says is a power p minus 1. Okay. Okay. I will tell you like this. So take a belongs to Z mod pz. Okay. So if you take a belongs to Z mod pz, what does the Lagrange theorem says? So pz start. Okay. So Lagrange theorem says the order of a divides Z mod pz star. The order of Z mod pz star. Okay. But which is basically p minus 1. So what it says is the order of a divides p minus 1. Okay. So this is by Lagrange theorem. So this is by Lagrange theorem. So what does that mean? That is a power p a times a power p minus 1. This is equal to 1. Okay, why? Because the order divides this, right? If you raise this to the power of the order, you have to get it equal to 1. But then this order divides p minus 1. Okay, so basically p minus 1 is basically order of a times some m will come, right? Because of the division. Uh, so in particular, this, if you look here, this is 1 power m and that is 1. Okay, so this is 1. So this is 1 in Z mod pz star. Okay. Okay, so what does this tells you? When two element in Z mod pz is same, okay. So what does it tells you? It tells you a power p minus 1 belongs to 1 plus pz. Okay, so this is what it tells you. So you can see here, right? From here, what you can observe. So a plus p minus 1 is equal to 1 plus p times n for some n. Okay, can you observe from here what we want to say? So now you take mod p on both sides, right? So if you take mod p, what you get? So see, you take this 2 number. What is the remainder here? The remainder here is 1. So a power p minus 1 congruent to 1 plus pn mod p. So, but if you take mod p, this pn, this is this is p, right? So this will be 0 actually. So p is congruent to 0 mod p. So this is kind of 0. So what is get is a power p minus 1 is congruent to 1 mod p. Okay. So here if you look, what you can observe is this a power p minus 1 is basically this number, right? So that means what is the remainder? If you divide by p, what will be the remainder? The remainder is just 1, right? So that is what it says. So this number and 1 has the same remainder when you divide by p. Okay. From here you can directly observe. If you want, you can just leave this step. Directly observe that if you divide by p, you will get the remainder as 1. Here also you get remainder as 1, and hence you have this. Okay. Now you just multiply a on both sides. Then you will get a power p minus 1. Sorry, a power p congruent to a mod p. Okay. So this is the Fermat-Little theorem. Oh, great. Okay, I think my pencil might have died. Oh. Okay, I think the pencil charge is gone. Sorry about that. So let's prove this one. So what we are going to do is we are going to use this particular group and to prove that Euler's theorem. So Euler's theorem also says the same thing as Fermat-Last theorem, but only difference is this is for any n. Fermat-Last theorem is only for n equal to p. So this is a little bit more general. Okay. So let's prove it. Let's say A belongs to Z mod nz star. Okay. Now what we know. So what is the order of this group Z mod nz star? So this order is nothing but phi of n, right? So you have an inverse if and only if the GCD has to be 1. So let's say you take 2 element here. Uh, so one of the important step here is to actually prove that the order is phi of n. Okay. So how do you prove that? So the actual step is what we need to do is it uses little bit number theory. So what you have to do is if you take a power I, so and it has to have inverse, right? So let's say in the modular arithmetic, uh, if you look at this equation, okay, this equation has a solution when this I is congruent to, sorry, this has a solution when this I is co-prime to n. Okay. So this kind of comes from the number theory. When you have this I is co-prime to n, so this has a inverse. Otherwise, it does not have inverse. So if you look at the Z mod nz star, Z mod nz star are all the elements which has the inverse, and the inverse only occurs when when this I is congruent to, sorry, this I is co-prime to n. Okay, so probably that is one statement. Maybe I'll just assume for now. Okay. Okay. Anyway, I think my pen has came. So okay, nice. Okay. So, but this particular statement, maybe I will assume it. Uh, but otherwise, I don't know how to prove it. I mean, one can prove this, but it's kind of lengthy, and I don't want to go into that. Okay. So maybe I'll just write here. Okay. Or maybe I don't even want to write x. I'll just write a. So inside, if you take the modular arithmetic, so this inverse means this, right? So that is another element to be such that AB has to be 1, right? So it comes from number theory that it is equal to 1 provided this A and N are co-prime. Okay. If it is co-prime mod, if these are co-prime, then you can write a B. Okay. So maybe if you want, I can just directly write the proof. Should I write the proof or not, or just assume it? Okay, maybe I will just write the proof. The proof, what you're going to do is you're going to use that Bezo identity. It's the identity in number theory, which says that if GCD of, let's say, A comma B is some D, then I can write D as N times A plus M times B. Okay, so this is the Bezo identity. So this identity I will assume. Okay, so this comes from the Euclid algorithm, Euclid division algorithm. You do the division algorithm, and as a consequence, you will get this identity, which is very standard. So this identity I will assume. Okay. So from here, what you have is if the GCD is 1, then what you have? The GCD is 1 means what? You have, let's use the Bezout identity here. Okay. So here assume that GCD is 1. So I will have, probably it should not use the same n. I will use alpha and beta. Okay. So what I have is 1 is equal to alpha A plus beta n. Okay. So that is what I have here. You can see from here. I'm just using the Bezout identity for this particular one. Okay. If you use it, now you take a mod n on both sides. Okay. So then what happens? Alpha A plus beta n congruent to 1 mod n, right? But beta n is just nothing but 0 because, you know, n divides this. So what you get is alpha A congruent to 1 mod n. Okay, so basically we got the alpha here. Okay. Provided if A and n are 1, we got the inverse. And you can do the other way around also. But for right now, I'm just going to assume that. Okay, so the other way also, if it is equal to 1, you can, so what we have proved is if it is equal to 1, then AB is congruent to 1 mod n. That we have proved. The other way also, we can write it. Okay, if you want to write the other way, how do you write it? Let's assume this one. We'll prove the GCD is 1. Okay. Let's say AB is congruent to 1 mod n. Okay. So what does this tells you? This tells you AB is equal to 1 plus some beta n, right? See, mod n means what? These two numbers give the same remainder, right? This two has the same remainder. So the remainder is basically 1. Remainder of AB, when you divide by n, is basically 1. But the quotient can be something. This is the quotient, that beta is the quotient. Okay. So the remainder is 1. Okay. Now we have this statement, right? So what we have is b times a minus beta times n is equal to 1. Okay. Now again use the Besode identity. So this tells you GCD is actually 1. Okay. So here, if GCD is D, then you can write this as this like alpha A plus beta B, where alpha comma beta belongs to integer. Okay. Moreover, D is the smallest such element. Okay, what does I mean by smallest such element? See, you take this A and B and you can vary the alpha and beta, right? So there are so many combinations you can put. You can put this as any integers. So you will get lot of numbers here. So what it tells is smallest positive such element. Okay. So this comes from Besode identity. So this you can prove using division algorithm. This statement you can prove using division algorithm. Uh, so I will just skip that part, how to use the division algorithm. But this is just a common property of GCD. If GCD is D, then you can write a GCD as a linear combination of alpha A plus beta B, where this alpha and beta belongs to integer. Okay, and moreover, this D is the smallest positive integer, such that the D can be written as the linear combination. Okay. So we just use the smallest thing here, because 1 can be written as a linear combination and 1 is definitely smallest positive number, right? So the GCD is equal to 1. Okay. So that is kind of the proof for this statement. Uh, so if you can just assume this statement, it doesn't matter. Okay. So what it tells you is this group, the element has an inverse if the A and N are coprime to 1. Okay, how many elements there are coprime to 1? That is the phi of N elements will be there. Okay, so that is kind of the argument. So the size is phi of N. So let's just use the Lagrange theorem. Okay, so if I take any A here, by Lagrange theorem, what will I get? What is the order of A? Okay. So now continue here. So the order of A has to divide the order of Z mod N Z star, but this is what phi of N. Okay, so that means order of A divides phi of N. Okay, so that tells you if you take A power phi of N, this is nothing but equal to 1. Okay, this is 1 in Z mod NZ. That is A power phi of N is equal to 1 plus NZ. Okay, I mean belongs to 1 plus NZ. That tells you A plus phi of A power phi of N is equal to 1 plus N times let's say some A, not A, some other B or something. Okay. Now take mod on both sides. What you get is A power phi of N is congruent to 1 mod N. So that is the Euler's theorem. Okay, so we have this, but I kind of assumed this Besode identity. I mean, ideally, I should have just assumed this statement. Uh, Instead, yeah, we can assume this and we can prove it. But I hope you understand the proof. If you don't, you can ask me always. Or you just assume this particular statement, okay? That will also work. Anyway, so what we have done is we have proved that Euler's theorem. So basically, once you have this statement, the Euler's theorem goes exactly like the Fermat-Little theorem. But see, when Euler and Fermat prove, they don't have the Lagrange theorem. So the proof is actually lengthy. That's why their names are also written there. But these are theorems But once you proved the Lagrange theorem, these are corollaries. Okay. So I'll just a little bit of a terminology I will tell. If you write lemma is actually a part of a small technical part of a theorem. So basically, see, theorem is the theorem. These are the things that we are actually interested in. Okay, and there is another thing called the proposition, which basically means proposition means something that is true. Okay, so usually we write proposition, but when the proposition is actually big and significant enough, we call it as a theorem. Okay, so lemma is also a proposition, but it is something that we need to in order to prove the theorem, and it may not be so much significant, or it may not be very hard. In that case, we call it as a lemma. Okay, and the corollary is a consequence of theorem. So if something that comes as an immediate consequence of theorem, that we call it as a corollary. Okay. So now if you look at these two statements here, this theorem, the Euler's theorem, and the Fermat theorem, these by itself are theorem. These are theorem because these are all very useful, as well as these are actually hard theorem when they proved in the earlier stage. But now once you have the Lagrange theorem, these things comes as a easy consequence of Lagrange theorem, and hence they became a corollary to the Lagrange theorem. Okay. So in that sense, you can see how the Lagrange theorem is useful. In number theory, these are big theorems, but I mean, in the elementary number theory at least, these are big theorem, but we can just directly prove it. Okay. Okay, let us come to the last part of today. That what we want to do is let's try to determine the last two digit of 3 power 3 power 100. Okay, so you can easily see that this is a hard problem actually, because 3 power 3 power 100, how many times you multiply 3 power 100 is so many. It's like 3 you have to put 100 times, and then you have to put 3 that many times. 3 you put 100 times, and then you multiply it that many times. You have to put 3 by brute force. You cannot do that. Okay, so there has to be a clever trick you have to use, and that is what we are going to use. We are going to use some modular arithmetic. Okay, so here's a hint: determine 3 power 100 mod 5 of 100. Okay, so probably I will give you 2 minutes so that you can think what exactly we have to do. So how do you determine that? I mean, they are telling you determine this, and they use the previous exercise, right? So what exactly we have to do? Okay. So anyway, I will give the idea. So first, let's think via the Euler's theorem. Probably I will copy it here. Maybe we'll go to a new page, fresh page, and we will start doing it. So what we are doing is we are going to use the Euler's theorem. So let's say, so what the Euler's theorem says. First of all, why the mod 100? See, I want to take last two digit, right? So what is the last two digit? Okay. So the last two digit, let's say you have a number n, number x. Okay. The last two digit of x is basically x mod 100. Okay. So this is the last two digit of x. So basically, divide by 100, whatever the remainder you get is the last two digit. Okay. For example, you take 999. Okay. Divided by 100. So this is what? 9 times 100 plus 99. Okay. So this is the last two digit. Okay. So basically what you need to do is you need to go mod 100 and find the remainder. Okay. So if they say last 3 digit, what you want to go? You want to go mod 1000. Okay. And last digit means mod 10 you go. Okay. Okay, so what you want to actually find is you want to find 3 power 100 congruent to whatever the question mark mod 100. So this is the number you want to find, and this number you want to be between 0 and 100. So basically you want this number between 0 and 99. Okay, so the remainder is between 0 and 99, right? So that is what you want to find. Okay, but what you have, we have, you take any number 3 power 5 of 100 is congruent to 1 mod 100 is known. You can look here. This is the Euler's theorem. Okay, so we are going to use the Euler's theorem. We will get 3 power 5 of 100 congruent to 1 mod 100. This much we have. Okay, see, if you look here, this is actually not a group theory problem, but I'm just telling it to say that group theory is useful in other areas also, in number theory also, in even in physics, etc. It is useful, but at least a number theory example I can say. So that's why just to give this a kind of like application. Okay, so this we know. Now what we have to do? Now what happens here is, if you look here, you have 3 power 100 we have, but here you have, if you do 5 of 100, this will be 1 we know. So if you write a 3 power 100, okay, is equal to some quotient time 5 of 100, okay, plus some remainder, then what happens? You write a 3 power 3 of 100. Okay, so this is equal to 3 power quotient time 5 of 100 plus remainder, right? I don't even need to write R1, I'll just write R. Okay, so this is 3 power quotient time 5 of 100 times 3 power remainder, right? Now what happens here is this will go away. This became 1 because 5 of 100, 3 power 5 of 100 is 1. So this will be 1. So this is nothing but 3 power R. Okay, what we have here is 3 power 100 is nothing but 3 power R. But what is the R? Okay, so what is the R here? From here you have to observe what is the R. So 3 power 100 is congruent to R mod 100. Okay. So what is this R? This R is the R. So this statement, you look this statement, take mod on both sides, mod 100 on both sides. Okay. So this statement basically tells you 3 power 100 and R has the same remainder. So they are congruent mod 5 of 100. Okay. Oh, sorry, not mod 100, mod 5 of 100. Okay. So that is the kind of hint that he is telling. Okay. So this is the hint he is telling, determine this particular number and use the previous theorem. Basically, why you look for this number is use the previous theorem. This is the number you will get here, and you are going to determine this number. So basically, we want to get this 3 power R, but let's find out what is the R. So 3 power 100 is nothing but 3 power R. So right now, our question is to find what is the R. Okay. Now look at what is 5 of 100. Okay. So 5 of 100 is nothing but 5 of 25 into 5 of 4. Okay. I'm not sure if you know that Euler torsion function. So this function, okay, if you don't know, I will just write a recall. Okay. So if you look at phi of n, this is actually this is a function, right? It goes from n to n, integer to integer. So phi of n is basically number of elements coprime to n. Okay. So for example, if you look at n equal to 5, then if you look at phi of 5, this is basically a coprime to less than n and coprime to n. Less than n and coprime to n. So okay. So if you look at what are the numbers, so phi of 5 is 4. Why? What are numbers that are coprime to 5 and less than 5? That is 1, 2, 3, and 4. Of course, we are always looking at the positive integer alone, okay, not the negative ones. So what is a phi of 6? Okay, let's look at what are the numbers that are less than 6 and coprime to 6. 1 will be there, 2 will not be there because 2 has a common factor with 6, so it's not coprime. 3 is not coprime, 4 is not coprime, 5 is coprime to 6. Okay, so this is 2. Okay. So basically look at all the numbers that are coprime to the n, and the number of such number, so size of the set is basically phi of n. Okay, so that's one interesting property about this. So this will split here. It will split like phi of n, phi of m, provided this n and m are coprime. Okay, if they are coprime, then you can write this is multiplicative. It's kind of like a homomorphism if you want to see, provided these are coprime. But otherwise, it's not multiplicative. Okay, and what we know is phi of p power n. Okay, this is nothing but phi of p power n minus uh, p power n minus 1. Okay, so this you can compute it. It's not hard, but anyway, I will just assume it for now. Okay, so let's compute phi of 100 here. So phi of 100. So if it is coprime, I can split, right? So 100 I will write as 25 into 4 so that it will be coprime. 25 times phi of 4. Okay. So what is phi of 25? 25 is basically 5 square. This is 5 square minus 5 times. And then this is a 4 square, right? So this is a 2 square. 4 is basically 2 square minus 2. Okay. And this is 25 minus 5. This is 20 times 2, right? So 2 square minus 2 is 2. So it's 4 minus 2, 2. Okay, so that is 40. Okay. Okay, now what we have here? We have it is equal to 40. Okay. So now I want to find this R. This is what we want. So, but we find what is phi of 100. So what we have is 3 power 100 congruent to R mod 40. Okay. Okay. So what we got is this mod 40. Okay. So this much we have, but still we are nowhere close to find it. But still 3 power 100 is still hard to compute. So let's do the same thing again. Okay. So what we know is the following: 3 power 5 of 40. We know that this is congruent to 1 mod 40, right? This we know. Okay. So let's compute what is 5 of 40. So phi of 40, I think you will compute here. I will just write it down. Phi of 40 is nothing but a phi of, I think this will be 4. I think it is a phi of 8 times phi of 5, I think, if I am right. Okay. And this will, if you compute it, you will get 16. Okay. So phi of 5 is actually, this will be 4 and this will also be 4. So you get 16 here. Okay. So what we have is 3 power 16. So we have 3 power 16 is congruent to 1 mod 40. Okay. So 3 power 100 is nothing but 3 power, I think it is 4 times 16 or something. Okay, 3 power 16 is how many times? Okay, so I just want to divide 100 by 16 and I just want to get the number. I think it is 6 times 16, I guess. 6 4s are 24, right? 36, 6 is 36. Yeah, so it is 6 times 16. So it is 6 times 16 plus 4. Okay. So this is basically what? This is 3 power 100 mod 40. Okay. Just 1 minute. Just need to do it. Okay, so this we have. So 3 power 100 here. Okay. So, but this will
Sir,
be
sir,
only.
once again I explain the steps, sir. 3 power 16 congruent to 1 mod 40, and then next step, how to write the next step, sir?
And so next up is 3 power 100. I'm just writing it as 6 times 16 plus 4.
Oh,
So 100
okay,
I'm writing as 6 times 16 plus 4.
okay,
So if you look here, this is nothing but 3 power 16 times 6 time is 3 power 4, congruent to 3 power 100 mod 40. Okay, but this guy will go away. See, because we have 3 power 16 is congruent to 1 mod 40. Okay, so this is congruent to 1 mod 40. So what we have is 3 power 4 is congruent to 3 power 100 mod 40. Okay. So now let's look at what is a 3 power 4. 3 power 4 is basically 81. This is congruent to 3 power 100 mod 40. Okay. So, but what is a 81? If you do congruent mod 4, this will be 81 is what? 2 times 40 plus 1 is congruent to 3 power 100 mod 40. So if you look at the remainder, so 40 will go away. The remainder is just 1. That is 1 congruent to. So basically, when this comes, this 2 times 40 is congruent to actually 0 mod 40. So this is 2 times 40 is kind of same as 0. So we can leave it. When you do mod 40. 100 mod 40. Okay. So let's see what we want and what we got. So this R is what we want, right? 3 power 100 is congruent to R mod 40. This R is what we want. And let's go and see what is this R. This R is 1 actually. Okay. Okay, let's go up here and where we have done it. Oh, sorry. Yeah. Okay, I forgot to write everywhere. I need to put mod 100. Okay. So basically, this is what? This is 3 power odd mod 100, right? 3 power 100 is nothing but 3 power odd mod 100, but we just figure out what is R. Okay. So we'll write it here. What we have is 3 power 100 is nothing but 3 power R mod 100. We just figure out that R is equal to 1. So this is congruent to 3 power 1 mod 100. Okay. So basically what happens, 3 power 1 is just 3. So if you look at the remainder is nothing but the 0, 3. So the last two term is basically 0, 3. Okay. Anyway, since we have did so much in between, I will just don't go into the detail. I'll just quickly tell. I mean, summarize what is the idea again. Okay, just to make sure, because we have write so many things, and yeah. So what we have to find, uh, what we want to find is, we want to find the 3 power 100 is congruent to what mod 100. That is what we want to find. But what we know is 3 power 5 of 100 is congruent to 1 mod 100. Okay. So if you look here, if you write it down by quotient and remainder, what you get is we get a 3 power r. Whatever the remainder we get, that is what we have. Okay. Because 3 power 5 of 100, we know it's congruent to 1. So let's write a 3 power 100, which is the term above. Write it as a quotient times 3 of 5 of 100 plus remainder. So whatever the remainder term is, all that matter. So now we move on to this equation and try to find what is this 100. Okay. So this, if you go mod 5 of 100, okay, so this equation tells you what? This equation tells you 3 power 100 congruent to r mod 5 of 100. Okay. This is what it tells you. Now let's find out what is that r. So here we compute that 5 of 100. So the 5 of 100 is 40. Okay. And this is again where it is. Okay. So 5 of 100 is 40. This is 5 of 100. Okay. So but what I know is 3 power 5 of 100 is congruent to 1 mod 40, I know. Okay. But what I need is 3 power 100 is congruent to r mod 40. I want to find this r. Okay. Now do the same thing again here. Okay. So this 100 you divide by 40 plus whatever the remainder comes, that 3 power r has to be here. Okay. So this we have, and but we need to find this particular r. Okay. So this we have, right? So this, if you look, that is actually equal to 16. 5 of 40 is actually equal to 16. So 3 power 16 is congruent to 1 mod 40. But we want to find what is 3 power 100. Okay. So 3 power 100 is basically, and then you just compute it, write it down here and you compute it. What you get is 3 power 100 is congruent to 3 power 4 mod 40. Okay. So this 3 power 4 is the r actually. Okay. So this 3 power 4 is the r. So but r you can write it as it's just 81. But 81 is nothing but you go mod 40. So r is okay. So you take the 81 and 81 you go mod 40, you will get r equal to 1. Okay. So that means 3 power 3 power 100, you can write like this. So r is 1 and then you got the remainder is 3. So basically you are doing the modular arithmetic twice. Okay. So probably you try to do by yourself, then you can try to understand why we need to do it twice. So once we are doing it once here. See, because there are two powers here. If you look here, there are two powers here. The first power I'm doing once, okay, and the second power I'm doing another time. Okay, so second times what we are doing, here we may do it again. Okay, so here we are using the theorem again. Okay, because there are kind of two times the power appear. So this for this we use the theorem once, and for this we use the theorem once. So you have to use the theorem two times. If there is a multiple powers up, then you have to use multiple times. But the idea is you just keep on using this theorem, and then eventually you will end up getting it. So probably you can try some other problem. If you try some other problem, it may not be always easy, but maybe I'll write one more problem for you as exercise. Okay, 98 power 9. Okay. Find let's say the last term. So when I say if I say last two term, three term, that will be usually be big actually. Last term means you just have to go mod 10. Okay, so this may be comparatively easier to find. So probably you can try this. Okay. Try 98 power 9, find the last term. Okay, take this number and find the last term. Keep it as an exercise so you can have an idea how to use that. So is it kind of clear? Okay, so with this we'll stop. And hey, you are the one who asked about that the problems, right? The find the number of homomorphism, etc. So hopefully the Lagrange theorem is done. Hopefully in some more time that other theorems are done. After that we will do a lot of such examples.
Sir, one doubt, sir.
Yeah.
How to find out the number of homomorphism between the groups and one-to-one homomorphism, on-to homomorphism? What is the procedure, sir?
No, those are not easy. Depending on the group, things will vary. So I will tell the general techniques. Okay, there are some general techniques, but depending on the groups, usually things will vary.
Okay.
Okay, but there are, once you've done the isomorphism theorem, you have some general tools which you can attack most of the time. But it's not see if you want to find out all the homomorphism between two groups, it depends on the groups, right? It's not something that you can do in general. Because if you have a cyclic group, it's easier. If you have abelian group, you can still do it. Abelian group is also kind of easy. In fact, see, until abelian group, you can kind of classify what are the homomorphism. So homomorphism group itself you can classify. But after abelian group, if you have a non-abelian group, you cannot do it. So probably in the tutorial, once a few things are done, I probably kind of tell what is the homomorphism of a abelian group itself. Okay. So maybe I'll just hint it out if you are interested. See, if you look at the homomorphism, this is the set of all homomorphism. From let's say you take Z mod nz to Z mod mz. Okay, this is actually isomorphic to Z mod uh, GCD of m comma nz. Okay, so this we can prove it. I think this is the correct statement. I think it is a correct statement. So we can prove it. After you have this, if you look at homomorphism of A cross B, comma C, so we can say this is isomorphic to homomorphism of A comma C cross homomorphism of B comma C. Okay, you can do the similar thing for this coordinate also. Okay, but if you have a abelian group, finite abelian group, one can prove that this abelian group is actually isomorphic to direct product of cyclic groups. Okay, so this is the probably we will do it by the end of the course if we have time. I'm not sure if you're doing it, but this is one of the important theorem, and it is called the uh, it's basically the fundamental theorem of abelian groups, finitely generated abelian groups. Okay, so this theorem says that every abelian group is actually direct product of cyclic groups. So once you have abelian group is a direct product of cyclic group, use this and this together. You can just say what is the homomorphism from a group from if you take from abelian group to abelian group, you can do it. But if you change this to a non-abelian group, it's not easy. Okay. So anyway, this we are not having these tools and all right now, so that's why I'm not trying to do it. But later we know all these things, and see if you want to find all the injective homomorphism, you just have to find what is the element of this element here, which are all invertible. Okay, so there are some such things you can do it, but right now let's not worry about that. But you can do it later. You can do it.
Okay. Thanks, sir. Thanks, sir.
Okay. Okay. We'll stop. Okay. See you. Bye.